Okay, so today's topic is quantum mechanics, continuation of quantum spin. So in last video we discussed about what is quantum spin, what it is. That just a recap. Spin in classical physics is all about what an object is doing that causes that object to have a spin. But in quantum mechanics or quantum spin is when it's about what the particle is. What particle is. Not what it is doing. What particle is. It being that particle is what makes it have that spin. That, for example, we knew that electron has a spin of 1 by 2. 1 by 2. Just because electron is electron and it is negative, it has this spin. It's negative because it's an electron. Positive, then we have a proton. Proton is positive because of its composition of quarks, which is proton is 2 up quarks and uh, 1 down quark. Okay, then when we also talked about IAM, and then we talked about what was it, angular momentum, the simple classical one. Okay, so after that, now today we will talk about an experiment. Today we will cover an experiment. For this quantum spin, and it's known as Stern-Gerlach experiment. Pardon if I said it wrong. Stern-Gerlach experiment. Okay. So here we will be using magnets. Okay, because electrons in somehow they behave like magnetic poles, so we will be using magnets, but these magnets have very special shape. And if I'm drawing it correctly, it should be this. And there's one down here. Okay, this has south pole, this is north pole. Okay, so and this is we call it a non-uniform magnetic field. So when we talk about electrons, they don't spin to produce angular momentum. If they were to do, they would have to spin or rotate millions and millions of times faster than speed of light. Okay, let's suppose we have an atom, atom of beam of atom. Yep, atom beam, and it's passed through these two magnetic poles. So what will happen here is that either it will either it will go up or down, up or down, up or down, up or down. Okay, but this experiment done with magnetic bar, when we talk about magnetic bar, magnetic sorry magnetic bar. First, we're doing the experiment with magnetic bar. There will be three scenarios. If we do this same experiment with magnetic bar, we will have three scenarios. First, we'll have a magnet facing up. Facing up means if we have facing up, facing up, facing up is facing up. It's south pole. Okay, so if it's facing up, then down, which is north pole, and at an angle pass through apparatus. Okay, so these certain situations: facing up, facing down, and at an angle, at an at an angle, at an angle, at an angle mean it has to be. Let's suppose it's at this. It's I think 45-degree angle. Okay, so then when we insert the magnetic bars in these positions, we will get three results. Bar magnet moved or pushed downwards by the stronger field of south pole. Bar magnet moved. Bar magnet pushed downwards by the stronger field. Okay, so it will be, let's suppose if it's going like this, and it will go down over here in this direction. This is first result. Second result, magnet moves upwards as north pole is attracted towards stronger south, because if the north pole is on the top, if this north is on the top, then it will attract the upper part of this, so it will be attracted to south and it will go up. And the second answer, the last answer, is bar magnet twist to align. So now at first we had it in either up, either south is up or north is up, but now since we have this situation in which it's at an angle, it's maybe let's put this south or north, it's at this angle, so we are not specifying either it will go down or it will go up. So what will happen is that the magnetic field will twist it, will apply a force, a magnetic field force, and it will make it twist and align the north pole with the stronger south pole. So the north pole of this bar magnet will align with south pole. Then consequences emerged from the magnet's distribution of position recorded by the detector. Means the consequences which we'll have for the positions of the magnets, either up or down or twisted to go up or down. First consequence is that first two orientations, up or top, down or bottom, We will have only either two options. We only have two options. Either the ball magnet will go up or it will go down. It will not go here, or it will not go in a certain, in any other direction angle. Then we have twisted magnets will fill the space in between. The twisted magnet will fill the space in between. Then for particles, now before we were talking about magnetic bar. Now we will be talking about particles. So for particles, it doesn't happen. It doesn't happen. Let's suppose mostly we take example of electron. Either up or down, any of these will take place. So either this point, either what we take it as is this up, this is positive up spin, negative down spin. Yeah. So for particles, it wants, it's all like that. Like this magnet, either it's in the top or bottom, or twisted to go top or bottom. But here it's distinguished. Either we will have plus 1 by 2 or minus 1 by 2, not here and there or anything like that. Then we have Larmor precision. Then it's a quantum. It's a spin is a quantum property. Okay, Larmor precision. What is Larmor precision? It's a key of the experiment. The experiment we talked about is the key of that experiment. And if I give a mean, if I give its definition, it's when I say, how can I say it? Precision or precision mean change in the orientation of the rotational axis of a rotating body. Mean the rotation, the point at which it rotates, change in that rotational orientation of the rotational axis of a rotating body with respect to its rotational axis. So then magnetic field wants to, here the thing is, magnetic field wants to twist the electron, or electron, we're taking particle as an electron, we're taking particle electron, just like it twisted the bar magnet. So here the magnetic field wants to twist the electron, but what happens that it twisted the bar magnet to align the electron's magnetic field with its own, but electron does not rotate, instead it precesses. What does it mean? Change in the orientation of the rotational axis of a rotating body with respect to its rotational axis. So even if the magnetic field wants to twist the electron, it doesn't happen. It, instead of it rotating, it just changes its rotational axis, the way it's rotating. So then we have torque. Torque is regarding twisting when we have rotational effects. So torque is what? Torque is result of a force that causes rotations. Result of force that causes rotation. Okay, so in formula it's and this is perpendicular distance per perpendicular mean 90-degree angle. Perpendicular distance, and this is force applied perpendicular. Acha. So then when we talk about in illustration, so here we can see the angle, this angle is 90-degree angle. So force applied perpendicular to the direction. So forces cause an object on an object to rotate, a torque is produced. So when a force is caused on an object, force is made on an object, the torque which is produced is rotate. So then this is where IAM, intrinsic angular momentum of the electron comes into play. Torque charges or changes the direction of AM. So torque changes AM. Torque is the reason for change in AM. Then here, this is one more equation. Okay, so this is one more equation which says that the new angle. Now we just talked about that torque results in change of angular momentum, and this is angular momentum. This is also angular momentum, but this angular momentum is new angular momentum, as we are applying torque. New angular momentum. This is old angular momentum, and this we know it's torque, and this here is time. Change in time. So this angular momentum is the this of torque and force. Now we will have a new angular momentum, and that angular momentum is regarding rotation, so it makes sense. And this is the torque. Sorry, this is torque. This is R, distance. Okay, then the intrinsic angular momentum of the electron traces out a circular path. So the electron's intrinsic angular momentum traces a circular path caused by the torque produced by the magnetic force trying to rotate the electron. So the IAM in the electron causes it to make a rotational circular path, which in result causes torque to be produced, and that torque produced by the magnetic force tries to rotate the electron. So then we have Larmor precision. Just a little summary. AM, angular momentum, changes the direction of the torque, which in turn causes the direction of the AM. For the separation, not separation, for the experiment. Here one more thing is that I should have written it on the top. For the experiment, the element used is Ag, and Ag is silver. Thank you.